Now we will study an extreme case of paramagnetism that is known as ferromagnetism. The ferromagnetism is the phenomena due to which an iron piece converts into a magnet. That means the magnetism in paramagnetic material, which was very mild, become very strong in ferromagnetism. Okay, we will see certain examples. This is one atom. All these atoms are there for a particular material. In this, when the electron moves, rotate, there is a magnetic dipole moment made. In this atom makes a dipole moment in this direction. This makes a magnetic dipole moment in this. This makes this. Now, what will be the direction of resultant magnetic dipole moment? You will say all will cancel each other because their number is very, very large. And it is a probability that for all the magnetic dipole moments in this direction, there will be many atoms having the moment in this direction and they will cancel each other. But not like that. In paramagnetic, you see these two are in the same direction. This will cancel out, but these two will prevail. So there will be a slight magnetism. This is paramagnetic material, which is not totally zero. It has a net dipole moment, but this net dipole moment is very weak. So this is the scenario in a paramagnetic material, and it has got a small magnetization. Okay. Now see the other situation. If all these, in certain materials, all these atoms which are making the magnetic field and which are creating a magnetization, all these align themselves this way. This on the same axis. So their magnetic field align themselves and they all add up in one particular direction. These all add up in one particular direction. Okay, what do we get at the end? I will just make it again clear for you, simplify it in this way. Okay, let us take it this way. This and this. There may be other set also. So all these are having magnetic field in this direction, magnetic dipole moment in this direction. These are also making magnetic dipole moment in this direction. Then there is another set here that is also making. Now we will see if their strength is very, very, very small. Even then, because all of them are aligned, their total strength becomes significant. This is property in certain material. Iron is such a material. Now all these atoms we have seen in such materials, they make a bundle, they make a group, and we will call this group a domain. So in this one domain, what do we see? That all the magnetic field is aligned in one direction. This direction we will call North Pole and this direction we will call South Pole. How large is this group? This group has got 10 to the power 11 atoms. Millions and billions of atoms aligned together, but atom is very, very small, 10 to the power minus 10. Okay, so what we get, an approximate size of a domain is to the tune of 1 millimeter. So a domain is group of atoms which align their magnetic dipole moment in one particular direction, and they have a clear-cut defined North Pole and South Pole. But they are very, very small. Their strength is very, very small. This we will call domain. Okay. Now these domains initially they are like this. This is a domain having north in this way, this is a domain having north this way, this is a domain, this is domain. All these are having magnetic dipole moments in different directions. What do? They automatically themselves make a group like this closed figures. Here is north of one domain, so here is south of the other domain. They attract each other. Then this is north, this is south, this is north, this is south, this is south, this is north, south, north, south, north, south, north, south, and they make a closed cycle. Here also north, south, south, north, south, north, south, north, and they make a closed. So similarly, I have made this figure, closed figure, closed figure, closed figure, closed figure. So all these domains initially are placed like this in an iron piece or in this material. What happens with this? You see, in a domain, this magnetic field is open. This magnetic field is open. If I put anything here magnetic, they have a power to give their magnetic field, to magnetize that thing. It has a magnetizing field open. Here, what has happened here? This is north, south. So we can say magnetic field goes like this, but this north get a south here, so it enters this. Now, it enters this because this north and this is south of this domain, north, south. It goes from north to south and again from south to north. No open end. Closed cycle. It is a closed cycle and no open end. And this is what you have to understand, what happens when there are open ends and when the ends are closed. Now, I have an iron piece here. I keep a magnet here and its magnetic field, in the terms of magnetic field lines, will attract it, will turn it, or will apply force on it. But for that, what I need? Magnetic field lines like this. But if these magnetic field lines, when these are going like this, it find another magnet here, they will enter here and go there. It will not reach there. So what I need? I want that this magnet should not be there and they should go all open like this. If it has got a magnetic field this way, this. Now if I put an iron piece over here, all these are attached to it and they will apply their force, do their action on this action. Okay, but now suppose I put another magnet here. This is north, this is south. I put another magnet here, it has got a south here and a north here. Now what happens? That this will go and turn this way. All these will turn like this, because this is a magnet and from here they will go like this. Now what happens to this iron piece? No action. I find in this no action, because these lines are not reaching it, and I will say this is not a magnet. But actually this is a magnet. We have kept something here so that its magnetism, its magnetic power, its magnetic field lines are converted or diverted to another direction, and I don't get it here. So if I want to get magnetization here, if I want to get magnetic field here, what should I do? I should remove this. Now there is no other go and this will come here. So what we need? that there should be an open end, and these lines should not have anything else, any other magnet in which it will go. That should not be there. But here we find that magnetic field north to south, north to south, north to south, and again to the north. Their cycle is complete, closed cycle, no open end. If there is no open end, the cycles are closed, so no magnetism. No magnetism. Now, next step. What we do, this we keep, suppose one method, we keep it in a solenoid and start current in that. When that current starts, a strong magnetic field goes in it because of that current in solenoid. This is solenoid and we are passing current through it. It is making a very strong magnetic field in this direction, and this thing we have put here. When we put here, then the magnetic field here apply a force on it. How? The magnetic field here, this north will experience a force in this direction, and this north will experience a force in this direction, and south will experience a force in this direction. There will be a torque acting on it, and because of this torque, it will move like this. It will rotate, and after rotating, this will be south and north. Similarly, this south-north, because of this strong magnetic field, north is allowed a force in this direction, south will experience a force in this direction, and they rotate. After rotating, they will become like this. Similarly, these are north to south, this is north-south in opposite direction. This magnetic field, which we are calling magnetizing field, that will rotate it, and it will be converted north-south. All the directions of all the domains will be like this. Now, we get the domains in this shape. I will make it here. Now, here are domains. Okay, now domains have aligned themselves under the force of this highly powered magnetizing force, magnetizing field H. Okay. Now they become like this. Now what's happening here? All these are having the properties of creating their own magnetic field, that is, in their own sense, they are small magnets themselves. What about the magnetic field created by them? That is represented by the magnetic field lines, and this will have magnetic field lines inside south to north, outside north, going to south, south to north, north to south, south to north, outside north to side, and this way. Here again, this, here again, this, and here. Now, if I put an iron piece here, what will happen? If I put an iron piece here, that iron piece is exposed to this magnetic field. I put it here, this is exposed to this magnetic field. All these domains, when these were of this shape, there was no open end and there was no magnetic field coming out, because all the magnetic field here was in closed cycle. They had a better medium to move. What was that better medium? Iron. These all are in this way, and they used to make a short circuit. So they used to make a short circuit, and their magnetic field are aligned this way, north south, and they make a closed cycle and it always searching, the magnetic field is always searching to reach a south pole by the shortest path. So this north has to reach this south by the shortest path, and the shortest and the best path is through this domain, through this domain, through this domain of iron pieces. So they will go like this. But if you force them to get themselves aligned, then there is no other go for them, and all the magnetic field will be here, and this is what we call magnet. Can we make all the materials like this? Answer no. There are very few materials who show this property, and those are the materials which are known as ferromagnetic material. Even paramagnetic material do not make domains. Paramagnetics are like this only, with a very few atoms showing magnetism in the same direction. But when it becomes very large like this, and there are small domains, this is property of the ferromagnetic material. This is the difference between paramagnetic and ferromagnetic. So you can make out the ferromagnetic is very strong. How strong it is? It is so strong that its permeability, that is relative permeability, is more than 1000. So much so. And if I make certain properties of it, I can make it, show you. If we have a magnetic field, okay, I would like to rub it off. If there is a magnetic field and I put a ferromagnetic material, only this much, that's all, 2 lines. The moment I place it here, what happens? When I place it here, then all these lines change their path. And now what we find, that magnetism inside it has increased manifold, and now these magnetic field can be represented like this. This way. So much good it is to get the magnetic field absorbed in itself. So all around it, all the magnetic field lines are passing through this. That means if we place a ferromagnetic material, all the magnetism around it would like to pass through this. This is very conducive for passing the magnetic field. What is the example of ferromagnetic material? Iron. Soft iron is the best ferromagnetic material. After iron, there is chromium, cobalt, nickel. These are also ferromagnetic material up to certain extent. Iron is the best. So this is ferromagnetism, and ferromagnetics material are used to make magnets. When we make magnets, there are different type of magnets with respect to their ferromagnetism, and this ferromagnetism can decrease, increase again with temperature. What happens when we increase the temperature of a magnet? What happens when we cut the magnet? What happens if we drop a magnet on the floor? These are the things we have to see, and that will be in the next lecture. Thank you.